Welcome everybody to the continuation of our energy efficient hot water boiler plant design seminar. And we're going to pick up now part 3, condensing system design considerations, and look at piping a little bit. We've been talking about condensing versus non-condensing, and I think we pretty well got in everybody's mind the market has moved to condensing products. But there are some different piping considerations and different design considerations that you need to be aware of. And I want to continue driving this concept of getting that return water temperature is so critical to you and getting it down. In order to do that, I'm going to walk through real basic comments on where do you put your temperature sensor for your whole system. Do you put it in the boiler supply side or the system supply side, or do you put it on the system return side? Where do you locate it? And I'm just trying to get you to fully understand we've got to look at return water temperature. It's critical if you're going to make a condensing application right in that boiler. We've got to have cold water coming back. So humor me for just a second. A real simple question here. Let's put it on the supply side. Let's put it on system supply side and see what happens at less than full load with the delta T and return temperatures, and ask the question, will the boiler condense? That's kind of the question we got to have. So here we go. If we locate the sensor in the system supply side, and let's say we set it for 140, and let's say we set it system supply side at 140, and we got a 20-degree delta T at full load, and let's don't worry about whether it's flowing variable or constant flow. Let's just keep a constant flow, take a snapshot. Here's my question to you. At 100% load, 20-degree delta T, full flow, we got condensing going on. We got 120-degree return water, supply is 140. Question is, what would happen at half load if we reduced the load to 50% and did not change the flow rate? We're going to keep the flow rate constant. I want you to understand the impact on the return temperature. So if we're holding a constant supply of 140 and we go to half load and we don't change the flow rate, what happens to the return? Obviously, the return temperature goes to half that of 20 to 10, so the return temperature is now 130. So the design was 140 to 120, you were condensing. At half load, same flow rate, you got a return at 130 and you're no longer condensing. So the point of it is, what happens to your return water temperature if you keep the flow rate up? Now hopefully we're varying the flow rate, but in case we were not, that's what would happen. What would happen if we went to the return side? What would happen if we just said, okay, we're going to control this in system return. We're going to hold that system return at 120. Because we know at 120 it's always condensing with natural gas is what we're after. Ask the same question. 100% full load, you'd have a supply of 140, you'd have a return of 120, and you're controlling to the 120. What would happen at 50% load in BTUs if I didn't change the flow rate? I'm going to hold the GPM constant. I'm going to hold the 120 return constant. So now the variable is going to be the supply temperature. What happens to the supply? Obviously 120 to 140 full load, 120 to 130 at 50% load, but we are still condensing because we're controlling the return water temperature at 120. Now we very seldom do this simply because of response time, so don't walk away thinking that's the answer. I just want you to understand the impact of where you put your controls and what happens. So the return water side would keep you condensing, but most people don't go there because of response time. Because once you fire the boiler, how long does it take that gallon of water to get through your whole system and back to the sensor? It might take several minutes, and you could be in trouble doing that. So the reality is, traditionally, and where we normally see the boiler supply water temperature sensor located is in the system. Traditional location would be system supply. But remember, we want to look at that load a little bit. We want to make sure we got multiple boilers running at colder water as possible at low fire. That's how you maximize the efficiencies of these systems. So how are we going to pipe these things up now that we kind of settled we're probably going to be controlling from the system supply temperature? How do we pipe them up? Do we have variable primary flow through the boiler? I see a lot of people going that way. We do a lot of them that way. We make them work. That's one option, variable primary flow. And we're going to show you a picture of that in a couple of minutes. The next option would be, let's have constant flow on the boiler side and vary the flow in the secondary. So in other words, we'd have primary, secondary, but the boilers would be constant flow and the load of the system side would be variable flow. Third system, and this is maybe a little new to some of you people, this is the way I believe it's really going to go. This is the most efficient way to go. Variable primary, variable secondary, where we're varying the flow through the boiler and we're varying the flow through the secondary at the same time, but we do have a bridge, so it is primary, secondary. Let's take a quick look at each one of these because there's some things here we need to be aware of as we work our way forward. So let's start with this variable primary flow concept. And great application, we can make it work. We got a lot of them out there. It's just a little bit sensitive to how you set them up and make them work. And let's just kind of see why. The concept is here, I've got one set of pumps. This set of pumps pumping through the boiler and through the whole system. So I got 3 boilers in parallel. I got a couple of pumps, as you can see from the diagram. And those pumps are pumping through all the heating coils, through the roll air trolls, all the way back, and we're pumping through the boilers as well. Now, how do we control those boilers? How do we stage those boilers becomes the question. So let's start off with the first question that you're going to have to deal with if you're dealing with variable primary flow with one set of pumps pumping through everything. And I switch you over to ASHRAE 90.1 2010 because of the energy code. This is what we're after. There's a very important piece in here you need to be aware of. Now, I think most of us are aware of the pump isolation on chiller plants, and that when you cut a chiller off, you're supposed to stop the flow through the chiller, and so forth. But a lot of people haven't really looked at the last paragraph, because the last paragraph of this slide very clearly says the same thing applies to boilers. If we have more than one boiler, and we go cycling the boilers on and off, that we've got to reduce the flow or shut the flow off when we cut a boiler off. Same concept. In other words, they don't want flow through a boiler that's not running. It's a waste of energy. Makes good sense, I think. You think about it that way. How do we apply this code? How do we make it work to variable primary pumped? Now, we're going to show an actual system schematic in a couple of slides, but before we get there, let's plant a few things in your mind, and these are must. If you're going to do a variable primary pump design, you have to do these things. I don't care who you are or what brand it is to make it work. You're going to have to make sure each boiler has a flow limiter so you don't overpump it. You're going to have to make sure each boiler has its own two-way isolation valve to meet the energy code of 90.1, 2013, by the way, 90.1, 2013, that's the same thing in it, that you don't flow through the boiler when it's not online, when it's not firing. You've also got to have a minimum flow rate for each boiler to start it up and staging, otherwise it's going to kick out on you on manual high limits. You must have a minimum system volume for each boiler. You've got a minimum gallons in the system so you don't short cycle it. It can get them started. And then you also must protect those pumps. There's going to be some minimum flow rate through the pump. We want to make sure we protect it. Those things you're going to have to do, and we're going to walk through each one of them in just a minute again, but get them in your head. No options here. These are mandatory things you got to do. So if we start looking a little closer at these two-way isolation valves that are on each boiler, what are the characteristics of these things, and what do we need to do here? Well, the first tricky part is they got to be timed to open and timed to close. You can't just stick a two-way valve and on and off. And that time to open and close is based on the boiler response time. So I cannot give you one answer for every boiler. You got to go to the boiler manufacturer and find out when he fires off on startup, how long does it take him to get up and running? Is it 30 seconds? Is it a minute before it gets under control? And when you cut it back off, how long does it take to get the residual BTUs out of that boiler back in your system so you don't waste them? So those two pieces on the time bit, in fact, most of the two-way valves would probably be provided by the boiler vendor, or at least get their advice on what time open and close. These must also be open when the pumps blow. In other words, section 2 here, one of these two-way isolation valves must be open when the pump's on so that you can take the residual heat out. In other words, you cut the boiler off, you don't quickly just close the valve, you leave the pump running for some period of time to remove the BTUs from the boiler and put them in the system after the boiler is cut off. So you got to make it run for some minimum time after the boiler quits firing to get those BTUs out of the boiler and put them in the system. So that time is based on individual boilers. You got to make sure you have that number. Third bullet point here, you want that pump interlocked with the two-way isolation valves to make sure you don't deadhead. In other words, if you initiate and you allow the boiler to come on and you're putting it in the heating mode, now the boiler may not be fired yet, but you're putting it in the heating mode and you want to circulate water through your system to allow the boilers to cut on and off automatically. Well, the only way you can do that is one of the boilers, even if it's off, one of the boilers minimum has to have its two-way valve open to establish a flow path. So you got flow through the boilers, through the system, so your system's in automatic mode. And you don't want to deadhead those pumps. We want the minimum from the pumps. Last bullet point here would be, we would recommend probably a few three-way valves out of the end would be ideal to establish that minimum flow for your boiler and our minimum flow for your pump, whichever is the biggest. But remember, we've also got to have one of those two-way valves on those boilers open at that point in time to establish a flow path. Let's bring all this together now with a little piping diagram. And here we go back to that variable primary pump schematic we had a few slides back. But notice we've added flow limiters. So each boiler has a flow limiter, and this means I can set it for the max allowable GPM through that boiler so we won't hurt the boiler. Second thing we've added is a two-way valve. Each boiler has its own individual automatic two-way valve, timed to open and close as we talked about, to make sure when that boiler's not being fired, we can cut it off. Now you see we got two pumps, and you also see a little bypass valve. That's a modulating valve here if you don't use three-ways. The next slide I'll show you where the three-ways would go. But you've got to have a flow path here, so when all the two-way valves on your heating coils are closed, there has to be some bypass to have minimum flow through the boiler and minimum flow from my pumps. And if you kind of look at it a little bit further, you can start understanding that, I hope. But do you need a boiler bypass flow path and modulating valve? You see the bypass in that slide, and the answer is absolutely you have to have one. So again, we're recommending that we go out in the system and put a three-way valve sized for the minimum flow rate for that boiler and or the minimum flow rate for the pumps, whichever is highest, and we make sure that we've got that flow path established. If you don't do that, you will have issues. Also remember, when we turn the pump on, the lead pump must run continuously to provide system flow. We have to have a flow path even if the two-way valves in the heating systems are closed. And we turn the pump on, we've got to have a flow path for them somehow. That's why, as you see in this slide, we are showing three-way valves at the very end of the system, enough of those three-way valves sized for minimum flow rate of one boiler and on the minimum flow rate of the pump, whichever is the biggest. That would be the ideal. If you don't want to do that, you can use the two-way valve we showed a few slides back in the equipment room and have to bypass around. Well, let's look at this slide a little bit further now because we've got the whole system on here. Think about enabling this system. The boiler's not firing yet. You want to put it in the automatic mode so that as you get a call for heat, the system can automatically cycle the boilers on and off. So if you enable the system, that means you're turning the pumps on. That means through one of those boilers, even though all three boilers are off at this point in time, there has to be a flow path. We have to have one of those two-way valves overriding, at least one, even with the boiler off, to establish a flow path for our pumps. And we need a three-way valve out at the end, so now we have a continuous flow path that we can flow with the boilers off, even with all the heating two-way valves closed. We do have a flow path that we can establish, and we can have a minimum flow for one boiler and a minimum flow from a pump. That's critical in variable primary pumps, and that's where people get in trouble, right there. If we don't do this, you will have problems. Please listen, because we do a lot of these. We're good at it as anybody you got, but when you start to commission these things, you got to make sure you have those flow paths, or you will have issues going off of manual high limits. Now, let's switch that over a little bit further and add in a bridge or common pipe. And we don't have time to do detailed primary secondary, but basically we're going to switch over and look at primary secondary. And the difference is there's a set of pumps for the boilers and another set of pumps for the system. And that little green common pipe relieves it. So this particular setup, we're using a dedicated pump per bore, and it's constant flow, and we've got distribution pumps that are variable flow. And we'll show a picture of that in just a second, a little more detailed. But the message I want to get across to you real quick here, make sure you don't miss this. I now have a pump for each bore. If I cut that pump off, there's no flow through the bore. If I cut the pump off in primary, secondary, there's no flow through the bore. I just met ASHRAE 90.1 energy code without a two-way valve. I just made it a lot simpler. Now my pump and my bore are tied together. They cut on and off together. Yeah, there'll be a delay in running to get the residual heat out of it from the bore, but the message is I've just cleaned my controls up a lot more simple. Let's take a little bit further look at this picture. Now here's the whole system again. Primary, secondary, I've got constant flow through the bores. I got a dedicated pump per bore. I've got a little green common pipe. So that bore pump just goes round and around and around in an equipment room. Then I have my roll air trough. I got a couple of distribution pumps that are variable speed. And you see I'm sensing the critical zone with a variable speed, varying the speed of my pumps back and forth. And you will also note there's a three-way valve out at the end for that minimum flow rate of my pumps. That minimum flow rate of my pumps. So let's back into this. What have I done? I now can set my bores up constant flow, and I don't need a flow limiter. And I don't need a two-way isolation valve for my bores. And I got constant flow because of that common pipe. I'm not worried about min and max flow of my bores. Once I set them up and do a manual balance to begin with, I'm home free. Let's go beyond the common pipe on the distribution side. Now I've got variable flow, and I have my three-way valves way out at the end to make sure I have the minimum flow rate for my system. The beauty of that is, to enable this system, you turn on the distribution pumps, the variable speed pumps, and they flow through the heating coils if they're open and through three-way valves around and around and around. So you've got your enabled on. You're not necessarily flowing through the bores yet. All those pumps can be off, and you're saving that energy because they're not even running right now, and you're not putting pressure flow through the bores. You're not wasting that energy. And they will only come on when you get a call for heat. So now you've isolated it, made it a lot simpler, and I think this makes a lot of sense. Now, if you start looking at it a little bit further and you start looking at details of this, what do you see happening here? What you see in a primary secondary system is that the supply water temperature is not quite as critical as in a chill water system. In which you can let it mix a little bit. Chill water, you don't want mixing too much, but in a hot water heating system, the little mix is not going to hurt you. In other words, it would be okay for your system flow rate to be greater than the flow rate through the bores. Your supply temperature would be mixed, come down a little bit, but it's not that critical. You can eliminate the need for the two-way bore isolation valves. That's huge. Those things can be tricky to set up, they're expensive. You can eliminate the need for the flow limiters. You get rid of those. Your controls are more simple and easy to operate. Boiler pumps will be staged on and off with a call for heating, and you save pump energy at night. They are constant flow, so therefore you're wasting some energy if you're fully flowing through the bores when you don't have full fire. That would be the thing that we need to take a look at. And guess what? We got an answer for that. The answer for that is, and I think the very future of condensing boilers is going to be variable speed primary, variable speed secondary. Can save you a lot of pumping energy. And to make sure you don't misunderstand that concept, let's look at it real quick. Now, we're back to primary secondary, but we made a major change here. Each boiler has a pump on it just like before, but instead of those boiler pumps being constant speed, they're now variable speed. Yes, we're going to vary the flow in a primary secondary system on both sides. We're going to vary the flow on the primary side of the water going through the bores, and we're going to vary the flow on the secondary side of the water going through the system with the two-way valves. Wow, that's a major change. But we still eliminated two-way valves. We still eliminated the flow limiters. We got the controls a lot simpler. And energy-wise, pumping energy, we're going to save more energy this way than variable primary pump. Why? Because when those bores are not being fired, there's no flow to cut the pump off. And if you're in variable primary pump, you still have flow through the boilers because there's no other way to make it work. This is the wave of the future. This is the way it's going to be. Pretty neat idea here. What these variable speed drives are doing on those boilers is they're going to match the flow through the boiler down to the minimum flow in each boiler to the load. In other words, if your load is 50%, you're going to cut your flow rate in half. In essence, what they're doing on the primary variable flow side of the primary secondary is they're trying to hold a constant delta T across those boilers. And if you go to a fire tube boiler versus a water tube boiler, the pressure drop through those boilers are 2-3 feet, extremely low. So now we've taken the energy pump-wise going through the boilers and just reduced it down dramatically to a low number. In other words, efficiency-wise, we're there. There's not much more you can do now because we're varying the flow through the boilers and we're varying the flows through the systems, and we're trying to make sure we keep the pump energy to a minimum. And we're using condensing boilers at 97-98% efficiency. You are really humming in on it now. So let's look a little bit at system turn down, multiple boilers, a little bit on control ideas, and what do they mean to us. Now remember, we want system turn down and multiple boilers because if we got 3 boilers at 33% fire rate running versus 1 boiler at 100% fire rate, we're going to be a lot more efficient with condensing boilers. We can push you towards that 99% efficiency if I got high turn down and I get cold water coming back and I make sure I got running multiple boilers at reduced fire rate. This is why this idea of cascading the systems makes sense. And most of your major condensing boiler vendors have a master control setup where they can run multiple boilers and run them on down at low fire to increase efficiency. And we would strongly recommend whoever you go with that you buy those and take a hard look at them because that's the key to getting efficiency of these systems. You're paying the money for variable speed. You're paying the money for condensing boilers. Codes are driving you that way. Let's make sure we take full advantage of it. In the old cast iron boilers of my generation, 40 years ago, we used 3-way valves. We had pretty much constant flow through the systems. They were big old cast iron boilers. They had hundreds of gallons of water in these big old cast iron boilers. They were huge. You go in the equipment room, they filled the whole room up. It was unbelievable how much water was in these things. We normally designed them on 20-degree delta T, so we had pretty big pipe, pretty high water volume. We didn't have the outdoor air reset numbers we got today. We had outdoor air reset, but it was nowhere near as much outside air. We would not. It was slow changing, so it was much easier to adjust on. The controls on these things are very simple. Most of the big old cast iron boilers had a simple Honeywell strap-on or insertion aquastat on them that maintained the boiler at some number, 150 degrees. So all the water in the boiler was hundreds of gallons of water in the boiler was 150. You didn't have any condensing problems. They kept them hot. They were simple. That was really simple. Now, specific heat, I bring this up because you know what it is. I want to get fundamental. And on the next slide, I think it's actually more important than this one. I'm just defining specific heat here. Let's look at the numbers for water. If I look at water, by definition, specific heat being 1 BTU is going to raise a pound of water 1 degree. So if I got a gallon of water, 8.33 pounds, then every 8.33 BTUs of energy I put in a gallon of water, that gallon's going to come up 1 degree Fahrenheit. And I don't care whose boiler it's in. I don't care where it is. It's going to be the same all over the world. That's a message you need to understand that. What's happening with the new systems? We talked about the old ones. This is the point I want to get across to. The new systems, we're going to 2-way valves, right? The code's making us go that way. 90.1 says you got to vary the flow. We haven't go to 2-way valves. We got a variable flow system. No questions asked. We made that change. The new boilers, though, have smaller heat exchangers, particularly the water tube boilers, really small. You may have a 800,000 BTU boiler that may only hold 10 or 12 gallons of water. There's just no water in there. Very low water volume. But these are ours as well. Very low water volume. We're going to higher delta T's on the design. We're no longer using 20. I see 30 about everywhere. I see a fair amount of 40-degree delta T. Why? We want cold return water temperatures on my condensing boilers to get the efficiency up. We want cold return water. It means your pipe sizes are smaller, means there's less water in there, less volume. So your pipes are smaller, the boilers are smaller. Begin to see a problem here. Fast changing loads. Now we got these sensors. We got a bunch of people in a room, and they come in the room. All of a sudden, they want so much outside air per person. So you quickly open up a damper to bring in outside air. So we got fast changing loads based on this new outdoor air requirements. And we expect our boilers and our systems to sense this quickly. That's what we're talking about, quickly, and respond. We also got more complicated boiler staging, and we're trying to modulate temperature control. So it's everything has gotten more complicated in newer systems. We've got to tie all of this together to make it work properly. Let's go back to my gallon of water. I'm trying to insult you. I want you to realize that a gallon of water in anybody's boiler is still a gallon of water. So if I put 8.33 BTUs in it, it's going to come up 1 degree. So here's what I'm trying to take you to. Let's take a typical system, and let's just use 180 as a set point. Set point could be 140, could be any number you want. How do you turn a system on and off? What is true delta T for the boiler in a system, and how does it set up? So let's just take a look at a modern boiler setup and make sure we kind of understand what's going on. Let's just take a set point of 180, and let's allow 12 degree delta T total. Well, that means if you look at the set point of 180, and again, it could be any number you want to. I'm just taking number 180. If my set point is 180, I'm sensing supply water temperature to the system. As that number goes up, my fire rate comes down. In other words, if the set point is going up to 182, I'm taking the fire rate down, on down, on down. And I've got to take it off somewhere. In other words, here's what's going on. If the boiler is putting more energy BTUs into the system than the load is taken out, then the supply temperature is going to do what? Start going up. And sooner or later, you've got to take it offline. So we're saying at 186, I'm taking everything offline. That my boilers are putting more energy into my system than I'm taking out, so the supply water temperature is creeping up. And as it goes up, sooner or later, I can't keep on doing that. I've got to take it offline. Now, if I'm matching the load with my boilers, if my boilers are firing at a rate that is exactly equal to the load of my system, which they're good at, my set point being 180, I can hold that set point pretty close. I can hold it 180, maybe half a degree. I can hold a nuts on that as long as I can modulate and put the BTUs into the system that you're taking out. So what I'm talking about is what happens when I'm putting more BTUs in the system than you can take out, and your temperature starts rising. Let's go to the other side of the set point. If I'm taking more BTUs out on the heating side than my boiler is putting in, what's going to happen to my supply temperature? It's going to start dropping. So sooner or later, as it drops, I'm going to have to bring another boiler on, stage another boiler. I'm going to be at full fire. So basically, I'm going to stage another boiler. So if I were to keep dropping there's going to be this cold water temperature that tells me I got to bring on another boiler. So I'm looking at a 12 degree on-off situation here, basically, so you kind of understand. I'm looking at 12 degree delta T, and when I drop to 186, I'm cutting everything off. If I get to 174, I'm adding more. And as long as I match everything, I'm about 180. So that's kind of the idea behind this delta T thing that you need to understand, because we have to size tanks. We've got to look at volume. So let's take a look at this thing. If I had a 2 million BTU fire boiler, typical 2 million BTU boiler, and I don't care if it's primary, secondary, or variable primary pumped, every boiler has to be started. And if you got a 2 million BTU boiler, and let's say that's the startup fire rate's 2 million, let's see what the start fire rate may be. In this case, I'm saying 30%. In other words, I'm saying I don't care what the turn down is on your 2 million BTU boilers. Most boilers will not start at turn down. Let me repeat that. Most boilers will not start at the minimum turn down. What am I saying is, you're turning a 2 million BTU boiler on. You got to go through a purge cycle. You got the fans that are going to come home, make sure there's no natural gas, and make sure everything is, all the air is in there. They're going to test all the controls. Then you're going to fire it up and get everything hot, and then you start modulating down. And that doesn't sound like it takes very long, but it can take 40 to 50 seconds easily. Let's assume it only takes 30 seconds. Now, you please stick with me, because this is one of the major issues we've seen with these boilers at low flow rates, and I think you need to kind of get it in your head, please. If you do this and you have a 2 million BTU boiler, And let's say at startup, it starts off at a fire rate of 30%. To be honest with you, most of them start off with a fire rate higher than that. Doesn't last long, but you don't start at the modulation reduced rate. You start at some fire rate based on the controls. So if I got a 2 million BTU boiler firing at 30% fire rate for 30 seconds, how many BTUs is that? It's 5,000, as shown on the slide. 5,000 BTUs you generated in 30 seconds. What could happen in 30 seconds? What could happen in 30? Sounds pretty easy, doesn't it? I don't care if it's variable primary pump. It's the same issue. I've got 5,000 BTUs I'm putting in this boiler in 30 seconds. At startup only. I can modulate down after startup, but I've got to get it cranked before I can modulate down. I've got to start it. So what does that mean? Well, supply temperature sensors and the temperatures on these boilers, they all have to have some time to work. On a direct sensor situation, I'm using 30 seconds. In other words, between fire rates and the temperature I'm seeing and the response time of the boiler, I'm saying 30. If it's an energy management system, building management system, it could be longer. It could be 45 to 60 seconds. You can take any number you want here, but these are very conservative numbers. I'm telling you, between the time you sit on the boiler to fire up and get going, there's some period of time before it gets under control. It takes a while to get it under control. So what happens in this 30 seconds is kind of the question. Let's just say we had very low flow rate through the boiler. Let's just say the boiler had no volume of water in it. No volume, maybe 10 gallons. Can't even really count it. No volume of water in the boiler. Very low flow rate of 10 GPM. What would happen in the boiler in 30 seconds? Think about it. What would happen? Let's go back. So every boiler has a minimum flow and a minimum system volume. Your boiler operating goal should be to do what? Fire for a minimum of 5 minutes, dry out good, run for 5 minutes, and be off 5. We want to make sure we don't hit this manual high limit safety, normally set at 210. The green safety control is a manual high limit, and we don't want a short cycle. Now, what's all this got to do with what I just showed you? Let's go back to my comment. All brands, no matter what kind of boiler it is. If your boiler's fire rate at startup is 30%, and it's 30 seconds before the modulation kicks in, which would be, again, low and conservative, on a 2 million BTU boiler, that's 5,000 BTUs. Where is that energy going? It's going into the water. You're putting 5,000 BTUs in the water. How much water does that boiler see if there's no volume in it to begin with in 30 seconds? Well, at 10 GPM, it will see how many gallons? 5. Right, think about that. So you're telling me 10 gallons per minute, it would only see 5 gallons of water, and I'm putting 5,000 BTUs in 5 gallons of water? What's my temperature rise going to be in 30 seconds? Would you believe 120 degrees? If your flow rate was 20 GPM, how many gallons of water would it see in 30 seconds? It would see 10 gallons. And you're putting 5,000 BTUs in 10 gallons of water because there's no volume of water to speak of in these little water tube boilers. There's very little water in them. Now you're over 60 degree rise. So that based on your controls, what would your manual high limit temperature do? It would kick out. At 10 GPM, for example, and your return water is 164, you see what happens? I'm at 284. So you are praying that it does kick out on my manual high limit, and that's what happens at startup. This is an age-old problem with people not understanding there's a minimum flow rate through a boiler to get it started. Boilers don't start modulated. They start at some other reduced fire rate to get it up and running, and people don't worry about it because it only lasts 30 seconds. Well, it can be an issue, as you can see. Repeating my numbers again, my 5 gallons of water, you see my temperature is 284, and you see I got an issue. So the answer was 284, 30 seconds was an issue, so I challenge you. If you will tell me, any boiler on the face of the earth, how you started up, what is the fire rate of your boiler at startup? I'm not talking about how far it modulates down. That's not the answer here. I've got to ask you, at what rate does it fire at startup? Number one question. Second question, how long? Does it take it 30 seconds, 40 seconds, 60 seconds? Now I've got BTUs. The next question is it having a volume in the system? To be safe, I think we better flow it at a rate enough to make sure we don't hit manual high limit. So if you give me those two numbers, the fire rate of the boiler startup and how many seconds, I'll tell you what your minimum flow rate is on your boiler. Any brand of boilers you want to call and ask us on, it's that simple. trying to keep you out of trouble. This is a major issue that people have really not picked up on. So boiler cycle time, we talked about cycle time and startup. It's two different issues really that tie together. You got to get the idea of the fire rate at startup at minimum flow. Now I don't want to short cycle my boiler. So let's look at, we are modulating the boiler down to whatever the minimum fire rate may be. What are your goals with a boiler to get long life out of it? You want your boilers to run for a minimum of 5 minutes. You go through this whole cycle, get them heated up. You want to run a minimum of 5 minutes. And in theory, if you ran 5 minutes, you'd be off 5 minutes, you'd have a 10-minute cycle time total, which would be kind of the minimum we like to see between on and off. So what controls your boiler cycle time? What controls the on-off numbers? It's very simple, really. It's the volume of water in your system that the boiler can see. The boiler has to be able to see those gallons of water, and the delta T between on and off. That's why I showed you a slide earlier about cutting off at, what was it, 186 and cutting on another boiler at 174. I was using a 12 degree. I think 12 degree delta T is a good number to play with here between on and off. Now remember, once the boiler's load and the boiler output match, we can hold very tight. We won't be 12 degrees. We'd be very tight. We're talking about on and off. We're talking about when do we turn this thing on, when do we turn it off, what is the delta T the boiler's got to play with, okay? So let's take a quick look and see where we are. So basically, if we kind of hold that delta T, here's a set of numbers and there's a rule of thumb that I kind of came up with using 12 degrees that I think you should keep in mind. Here's your calculation, so keep it simple. Every 100 gallons of water in your boiler and in your system total that the boiler can see can hold 10,000 BTUs at a 12 degree delta T. In other words, you got your boiler at 186, you cut it off. The boiler stayed off until the temperature dropped to 174, and you brought it back on. Repeat that. Your set point was 180, but the boiler goes off at 186, and at 174 it comes back on. That's a 12 degree delta T between on and off of your boilers. You can take that 12 degree delta T, and for every 100 gallons of water in your system, you can store 10,000 BTUs. Now you begin to see how these buffer tanks need to be calculated and how we're beginning to take a look to stop short cycle. And this is very simple. That's why I like the 12 degrees. It's an easy rule of thumb to hang on to, and it's a good practical number between on and off. I'm not talking about operating temperatures. I'm talking about between cutting on and off of your boilers. So if I take that concept a step further, here's a little situation where I've got a 1,000,000 BTU boiler, and that's going to be my minimum fire rate. It's 1,000,000 BTUs. It's a big boiler. Turn down it's only to 1,000,000, so turn is not real good, but it's 1,000,000 BTUs. It'll be my minimum modulated fire rate. Could be 100,000. Whatever number you got is a minimum fire rate. I'm going to use 12 degrees here. I'm going to use a 12 degree delta T. And you walk through the numbers, my 5-minute run time, minimum fire rate of 1,000,000 BTUs for 5 minutes is 83,000 BTUs. If my turn down was 100,000 BTUs, I would only have 8,300 BTUs to get a 5-minute run time. In other words, I want to make sure between on and off, between 12 degree delta T, I can put 83,000 BTUs into my system to make sure it runs a minimum of 5 minutes. And that's going to take, if I use 12 degree delta T in 10,000 BTUs per 100 gallons, it's going to take 833 gallons of water in my system to make sure that a 1,000,000 BTU fire rate runs a minimum of 5 minutes. Now, that would be a big system, I agree, but all you got to do now is calculate the volume of water and everything, make sure you've got 833 gallons. I'm just trying to walk you through an example. So here's the actual formulas for runtime. Now, I'm not taking advantage of what I just said in the load. I'm just assuming there is no load. Because I like to calculate these things as if there is no load. Your runtime is there, your off time is there, you got your BTUs, and you show your pipe sizes to come up with gallons per foot to estimate the gallons of water in your system. Well, again, we recommend 5-minute minimum runtime. We're going to assume it'll be off 5, so we got a 10-minute combination here that's kind of the minimum we'd recommend. You can make yours anything you want. We're just giving you something that's practical that most people will support. So by putting all this together, you might need a buffer tank when you do these calculations to get this extra gallons. again, if it's a water tube boiler, you probably will need that buffer tank because there's very little water in the boilers to begin with. If you have a fire tube boiler, it has a lot more water, but we still need to do the calculations. We've got to sit down and calculate it and make sure. And again, that delta T and the volume is the key. What delta T you're going to set your boilers on to cut on and off. On, off, delta T. That's the key to how many BTUs you can store to handle in short cycle. The higher the delta T or the higher the volume of gallons of water, the longer runtime I can get, the more I can kill the cycling issue. So you kind of see the buffer tank idea. Let's kind of bring this together because we've made a long journey here. Let's just make sure you're on board. On heating systems, basically, you want to keep the return temperatures below 120. Your pitfalls might be very simple. If you have a heating system that shows water above 120, you've got an issue. We're trying to make sure we got that straight. I have to figure out how to, hang on one second, please. Not sure what's going on, but I think I've got an issue here. Heating system would reset above 130. Would be a problem because we're not going to be condensing. If we had indirect heating where we had domestic water tied in with the boilers, we might have an issue because if you want 140-degree domestic water, that means your boiler temperature has got to be above 140, and how are you going to condense if you got 140? So those are issues you really don't want to play with. Ladies and gentlemen, I appreciate your time, and have a great day, and we have come to the end of our condensing boiler seminar. Take care.